Okay, we're recording now. So let's begin. So today we're going to finish this kind of section on evaluating which kind of model function, like function class to pick. And we'll see that there is like, so far we kind of covered this discrete way of picking like polynomial degrees or picking different function classes. We're going to, today's class, kind of see like a smoother way to kind of do this. And afterwards, we're going to get into, I guess, this topic of doing kind of machine learning, like doing something other than, I guess, empirical risk minimization, which we're going to call this like way of estimating probability, mass, or density functions, which we'll see actually turns out to be equivalent to empirical risk minimization under certain conditions. And the names for this is called like maximum likelihood estimation and maximum a posteriori, which are just methods to estimate a distribution. And we'll see why we would want to do that instead of minimizing the empirical risk. But before we get there, we'll just wrap up this section and maybe we'll get started on that today. Okay, so let me remind you how we are doing this whole like selecting our function class basically for using for ERM. And the idea is to decompose where is our error coming from and then try to understand where it comes from, and that will give us some kind of insight on really what function class we would want. And yeah. Okay, so this, I think this picture is quite informative, hopefully. And it tells us where our error is coming from. And in particular, kind of the thing we actually produce after learning from data, the thing our learner produces or outputs, is a predictor. And that's like this f hat of t. And the capital T, I guess I'm making very explicit here that you're running like gradient descent and that you've run it for t epochs and you've output a predictor. And it has some like expected loss. And that might have some error. Well, okay, that's a number, and we want to make that as small as possible, because if that's 0, that means you've perfectly labeled all your points. And by points, I mean that means you perfectly labeled any new data point that you're going to get. Okay, so if this value is 0, that means you get any new data point, you perfectly predict the value. That's the best you can ask for. So you want to make that small, and you try to understand where is the error coming from when it is non-zero, which it often will be. And based on that error, you can figure out what things contribute to the different errors. And then based on those things, you can try to like improve certain aspects of the learner. Okay, so the first kind of error is this optimization error, which really is, we're not going to talk much about in this course. It's not even going to be tested really too much, like in this explicit way. But it's good to know, which is that the error is going to come from just optimizing using gradient descent. And like you run it for some finite number of epochs, which means you're not going to quite get to the true minimizer all the time. So that'll be like this error here. And this f hat here should be thought of as the true minimizer of the empirical risk. Okay, so there'll be some error there. Then afterwards, what we've really been focusing on is if we even had the true minimizer of the empirical risk, where is the error coming from? And there we saw, well, some of the error is coming from the fact that we're using data, right, to estimate the risk instead of having the true risk. We don't have access to the true risk. Instead, we have this L hat object. And that is an approximation to the true risk. And since we're minimizing that, hence the empirical risk minimization, there's some error. And that's called your error in estimation. It's estimation error. And it's really because you're using a proxy, an estimate of the true risk. Right, F hat is the minimizer of L hat. Yeah. Okay, and then the next error you can think of is like, well, we chose a function class. And so even if we minimized like the true risk, the expected loss, the true risk, what is our error? And this is the error due to the fact that we chose a function class, and that function class might not contain the best function for labeling our data. And that's the error here between this and this term. It's called the approximation error, the error in our function approximator, people will call it. And that's really just the difference between this f star, which is the best function in our function class for approximating new data, compared to the best possible Okay, come on. The best possible function you could ever pick, which is f Bayes. And then finally, there's this error that you might still even have if you pick any function and you knew the true risk, which is just due to the inherent noise, or the fact that, like, if you just look at one, like, x value, there may be multiple possible labels, which we've seen is very reasonable. You might look at a house with some number of rooms or distance to downtown and so on. You can imagine there's many houses that satisfy these properties, and they probably won't have the exact same price. Okay. And we mathematically just wrote this down by adding and subtracting the terms, which is like, this was the error in estimation, this was the approximation error, and this was the irreducible error. And we plotted them. And the plot looked like this. So the three things to look at are kind of this orange line, which is the error of our actual predictor we're going to output. The green line, which is the error of kind of the best predictor in the function class, if we knew the true risk. And the black line, which is the best error you could ever hope for. So you're never going to get better than this black dotted line. And so really you want to drive this orange line as close as possible. You want to make this orange line as close as possible to the black line. And we saw that there's competing kind of effects going on, which is that if you make the function class big, which is what the x-axis is here, well, then the best function in your function class, this kind of green line, is indeed approaching the black line, and it can at some point reach it, and it'll just stay at exactly this point forever onwards. However, the competing kind of issue is that if you make the function class bigger and bigger, your estimation error will go up, which is this error here. And that goes up because, roughly speaking, you only have like some finite amount of data, and you have a bigger and bigger set of functions to kind of pick between or distinguish between which one is the one labeling it. Okay. And so that's going up here as we see here. And we want to find kind of like this balance, which is this like just right point. And the idea is that if you're too far on the left side, which is your function class is like not complex enough, well, then you're going to have a large approximation error, a small estimation error. And this is called underfitting. And on the other side, where you have a really complex function class, but you don't quite have enough data to distinguish which function is the one labeling the data, you have a large estimation error, and this will be called overfitting. And so in terms of picking the function class, you kind of want to pick this point. And if you want to drive this curve any lower than this point, what you're going to need to do is gather more data. And what gathering more data will do is it will drive this point closer and closer to the best possible point here. And that we saw in this plot where you gather more data, and you find that indeed the thing you output will be closer and closer to the best possible thing you output, because you basically see like what is almost all possible data points. And so this orange line is going to here. And you also find that your empirical risk, the thing you're actually minimizing, is also approaching this orange line and getting closer and closer to the best possible. Okay, so that's all review from last time. And then this like estimation, approximation error view of things is one way to think about it. And another way to think about things is this like bias variance error terms. And people call this like the bias variance trade-off. The above you could call like the estimation and approximation error trade-off. And people like this bias variance one because in some way, when we get into just in a few minutes, we're going to talk about this thing called regularization. It somehow is a little bit nicer to discuss there, I guess, is one reason why. But it has a very similar flavor. Okay, so how does this work? Well, it's going to work very similarly to the approximation and estimation error. So at the end of the day, you still want to make the expected risk small of the predictor our learner outputs. And we want to break it down into error terms, and we're going to break it down into a bias and a variance error term, plus the usual irreducible error. So far all I've done is the same thing as we did earlier. So let's just go back up here. I've taken this term, and all I've done right now is I've added and subtracted the irreducible error term, or the risk of the Bayes optimal predictor. And now instead of adding and subtracting this kind of term, there's a different procedure you do. And the term we're going to care about is not f star, where f star was the best function in our function class for minimizing the true risk, the true expected loss. Instead, the quantity we're going to kind of compare to is now called f bar. And the bar is to kind of indicate, usually bar means average, kind of like the sample mean thing. So people use this and they call it the expected predictor. And the expected predictor is just the predictor you out. So you predict, your learner outputs a predictor. That changes with data sets. Well, you can take the average predictor, so you can fix a single point x, that's what this conditioning means. And you can look at every single predictor you'd output, depending on the data set, and take the average kind of value. Okay, so maybe we should draw a plot for that first. I think that will be helpful to understand what this average predictor might look like and see how it varies as data changes. Well, okay, the expected predictor doesn't, but the actual predictor does. So let's just draw this. And let's continue with the previous example that we were doing a bit earlier on. And so I'm just going to take this plot here. Okay, I'll take this plot, and we'll see what happens. And maybe I'll take this part of it as well. Okay, so for now, we're going to remove. Actually, let's keep this. So this green thing was f star. If you remember, this was the minimizer of the expected risk or the expected loss, the risk. And this orange guy was just a specific predictor you get if your data set was these orange points, right? And then we talked about, and maybe I should have just took the other plot after this, but then we talked about what happens if you get new data points. And you might get new data points that look of the form, okay, I don't know, something like another 5 data points. Maybe they look like this. And then your learner would probably output maybe a different line. Maybe that line looks like that. It's similar, but not quite the same. And then you could get like another 5 data points. Maybe you get these points. I don't know. This line might look like that. And the point is, as data set changes, the predictor, the model you output based on the data set can change. Okay, then there is the average, this expected predictor that we were talking about. What is this thing? Well, this thing says, fix a particular x value. So that would mean like, I don't know, fix this x value, for instance. And then look at all the possible predictors you would get. So like over all data sets, so like this green one and this purple one and this orange one, and you do it for all possible ones, over all possible data sets. Take their weighted average based on the likelihood of getting those data sets, right? That's the expected value out here. And then f bar will just be that value at that particular x point. And you do that for every single x point, and you get a new function called f bar. So like for this point, you would go like, okay, take this guy, take its weighted average, and do it for all these guys, and you get a point. Turns out that the function you end up getting, so far everything we've studied, f bar actually equals f star. And so the average predictor will look actually exactly like f star, and that should make some sense. Some data sets will cause you to like be slightly above the bright green line and then slightly below here, while other ones, maybe you're like the other way around and so on. It turns out to average out to be exactly like f star. And so far for everything we've seen, this f bar is indeed actually equal to f star. And yeah, in general, this is kind of the property you see. Okay, maybe I'll put equality for now because this is indeed true so far. Okay, great. So that's how we think about the expected predictor. And you can see now that like any particular f hat, like this orange guy, this purple one, will vary relative to f bar. And I'll take the question in a second. And so you might want to ask, what is like, how much do they vary relative to f bar? And then the other question you might ask is, as we've kind of seen, is how far is f bar kind of from this f Bayes equation? Okay, and it turns out instead of adding and subtracting the risk or this L term of f bar, we're going to do it in a slightly different way. And before I do that, I'm going to take the question. Yeah. Oh, so by fixing, I just mean this is a function of x, which means for every single x, it takes a value. Okay. So I need to tell you, how is this function, like what value does it take for every single value of x? Okay. And the procedure to get that value, right? Because f bar, once again, is going to be, it's a continuous line like this. And every single value of x, it takes on some value. And I'm just telling you a way to interpret the procedure to get the corresponding value that it takes. And that procedure should be thought of. For the corresponding x, and I mean, technically you should write it like this. It's like the random variable x equal to little x. You fix that little x, and then you take the average value of all the predictors you output based on the data sets. So you take the average value over all data sets of the particular point. So like if you'd say, I want the value of f bar at x here, I'd be like, okay, what you need to do is you need to take the weighted average over data sets of all the f hats you would output based on the data sets, and then calculate that point, and you would get just the single value of f bar of x here. And you repeat that process for every single value of x when you need to predict. So it's for every value of x, you need to redo this calculation. That's how you should think of it. Yeah. Okay. And so now to make this decomposition very clean, which is what people will do, and it turns out to do this, we have to use the same assumptions we've kind of been making up to now, which is we're going to assume we're still in the regression setting. So if you're still doing regression, meaning your labels are these like continuous things with notion of order, and you assume the squared loss. This is important. So you're using the squared loss. Well, then, it turns out that you can rewrite the above error. So what we're going to do is we can rewrite this thing as follows. We can rewrite it as a bias and a variance term. Okay, so first we'll do the variance term, and the variance is kind of like the estimation error. And roughly speaking, it's going to be how much f hat varies relative to f bar, right? Okay, and so that's going to look like this. So let's do the inner expectation first. So you want to know how much does f hat, which is a function of data, right? How much does this guy vary relative to f bar? And you should think of this as like an expected value, and this is your random variable of d. And then the variance has a squared term. It's square, like it's the squared deviation. And you can see naturally this is going to come out of the fact that we're using a squared loss, and that's why it's really nice. And so this is the variance of our predictor, but at a particular point x. So this actually turns out to be something called the conditional variance, which we won't worry too much about the like specifics of how to get this and stuff. It's just trying to build the intuition. So now you have this kind of conditional variance, and so we're going to need an expected value around this whole thing. Okay, and this would be like the conditional variance for a particular value of x. And then finally, since we're interested in how this varies over data sets, you have an outer expectation over data sets. Or sorry, over x. Inner one, of course, is over data sets for a fixed x. Outer expectation, the only thing that's left that's random is this x. So then you take the expected value over all of your data points x. Okay, so this is your variance term. And I'll make some more room so we can see the other terms. So this guy is called your variance. And this is exactly the conditional variance of this. And the other term is the bias. And the bias is going to be the difference between f bar in squared error relative to f base. Okay, I guess I'll need some more room again. Maybe I just shift this to the left a bit. Okay. Then you have this bias term. And the bias term, you just want to compare f, the expected predictor, relative to f base. Okay, and these are like your random variable x's. And you're going to want to compare it in squared distance. This is like the squared loss part. Once again, if you did not pick the squared loss, you wouldn't have this nice decomposition like this. And then you just want to know what is, on average, this error, and in particular, like a weighted average over new x points that you would expect to get. And so that's, you take this expected value of this over values of x. Okay, and this turns out to be your bias term. And bias has a very specific meaning in statistics. It's like how far you are from like the true expected value of your estimator and stuff. But in the English word, I guess, sense, it also makes a lot of sense. It's like how far is this expected predictor like biased away from the optimal predictor f Bayes. Okay, and in what we've been studying so far, this turns out to exactly equal the estimation error, and this exactly equals the approximation error. And of course, what is left is that so far these terms were just the decomposition of this. Right, you can already see kind of like this term, this f hat was here. We kind of added and subtracted f bar, but turns out you do it when you in the inside, when you expand the expectations, and it's a bit of a complicated derivation. We're not going to go through it. And then f Bayes is over here. So you can kind of see how this would make sense, like f hat plus minus f bar minus f Bayes, and then what's left is to still include this term. So of course we got to account for that. And so that's going to be still added here. Okay. And so that's another way of interpreting kind of the error that you get from, I guess, different function classes and how much data you have. So, and visually it should be thought of like what we were seeing here, which is that, yeah, so the variance is like how much do these lines vary relative to f bar? How does any particular predictor, as you change the data set, vary relative to f bar? And then the bias is how far is f bar relative to f Bayes, kind of, but in squared error. Okay. Maybe one more plot to kind of see, and we've plotted this before, so maybe I just take it, is this variance can also be thought of as, you can see it here. So like this is a perfect example of why increasing the function class would increase your variance, which was equivalent to saying our estimation error went up, right? And we can see now that if we interpret it as above, which is this green line is f bar, it's our expected predictor, well, then we can see for any particular data set, as the data set changes, how much we vary relative to the green line is quite a lot. And this is because our function class is very rich. So you change the data set, this purple line is quite different from the green line. Then you change the data set again, the orange line is quite different from the green line. While for the lines, you can see, for the case where the function class is just lines, you can see they don't vary that much if you change the data sets. So that's the kind of picture you should have in mind. Okay. And yeah, and the kind of relationship is what we've seen before, which is the bias will go down, right? This is like your approximation error if your function class is richer. So if like, I'm just gonna like, if your function class becomes more complex, and we see that here, right? You get more complex functions, the green line is much closer to the black line. The squared error between them at every single value of x is much, much smaller. That's all that this was. This was a measurement of the squared error for every point of x. Okay. And same relationship as we've seen for approximation error. And the variance has the relationship that the variance will go down if the number of data points goes up. Also makes sense. If you added way more data points, so instead of having these 5 points, you had way more, then it's unlikely that these lines would be like so dramatic. They could be much more close together, like similar. And if the variance instead, well, you can make the variance go up, which you don't want, of course. And that will happen, unfortunately, if your function class increases. So again, we see this kind of trade-off here, which is you make your function class more complex, your bias goes down. You can get closer to f Bayes. But if your function class gets more complex, unfortunately, you suffer higher variance, meaning that if you were to see any new data set, then your function would vary quite a lot, or it basically has this kind of overfitting behavior. Okay, and you can also plot this kind of same idea with underfitting, overfitting sort of business on like a test set if you wanted, and you can do the same procedure. And so maybe I'll take that as well from before. Okay, let's just do it for the test set case. Okay, never mind. Okay, maybe I won't. Okay, like remember this picture. I'm gonna draw it again with just the orange line, and then we'll do the same kind of labeling. Okay, so you had the polynomial degree at the bottom. This was like 1, 2, up to whatever, 7 or something like that. And we had this orange line that looked something like, okay, let me just draw the curve. It would look something like that. You had your points, which is the predictors you produce using ERM for these different degrees of polynomials. And what you should understand is if you plot this thing, which is, right, we're plotting, I just copy and paste it. We're plotting this term. It's the thing we really care about. It's the expected risk of our actual predictor. Well, what you should interpret from this above relationship, like basically this thing, is that if your error is going up, or first of all, if your error is small here, or sorry, let me say that again. This is the error you care about, your expected risk. If the error is large, well, then this is likely due to the fact that your function class is not very large. It's the case where this was very small, and so your bias was very high, right? You can see it in the inverse case, like increasing this would make the bias go down. So small f would cause the bias to go up. So here you have large bias. So here you have what is high. In this side, you have high bias, probably low variance, if you have enough data, or if you have some sufficient data. And this would, similarly, people call this underfitting. So if your bias is very high and you have low variance, you've underfit. And that looks kind of like this line thing where f bar is underfitting. It can't even represent f base. Okay, and then on the right side, we're going to have the overfitting case. And that is when what happens? Well, our function class increases. And when our function class increases and our error is large, that is likely due to the fact that the variance went up as our function class increased. Because if our function class increased, our bias would have went down. And so on this side, you have probably low bias now and high variance. Okay. So similar story to what we've seen before. Okay, that's all I have to say about this. Now let's discuss about how to kind of more smoothly choose the complexity of your function class that's not just like a discrete polynomial degree or something like this. Okay, and that idea is called regularization. And this is actually what is used in practice instead of, most people do not just train like a bunch of different polynomial degree function classes or neural networks of different sizes. You'll probably fix your size of your function class, and then you'll use this parameter called your regularizer, and you're going to sweep over values of that, which are somehow going to change the complexity of the function class. Okay, and here is the idea. So first, let's make some observations about what the weights or parameters of a polynomial kind of mean. Okay. So this is just like some random plots first to kind of understand what the weights, how they might affect things. And by weights, well, you'll see what the weights are, right? So maybe you plot like a line. Okay, so like here's one line. Maybe this is like, I don't know, like 1/2 x. And don't worry, we're going to get to the function class thing. So far, we're just building intuition of how like the weights, with the weights, remember the weights are parameters, are things that multiply. So let me just remind you what these weights are. So the weights are like you have a function like f hat of, let's say, x, and maybe it's something like w0 plus w1x plus w2x squared plus w3x cubed. Maybe you chose polynomial degree 3, you ended up with this thing. These are the weights. And it turns out that the values these weights take somehow will dictate the complexity of our function, okay? That's what we're trying to build some intuition about. And then we're going to see that if we tune kind of the values, if we have like a constraint or like a penalty for making the weights really large, we're going to see that somehow that's going to tune the complexity of the functions we're allowed to output. Okay? So let's just really briefly build some intuition of this. So like with a line, you have like, I don't know, 1/2 is your weight here. And maybe you have like this y-intercept, I don't know, maybe it's 1/2 as well. Okay, and that's like, these other ones are 0, these other things. And okay, like you add these up, it's like 1, you know, you don't have any weights here. Maybe this isn't that complex. Let's see what, like, if you change this slope, well, then you get like a steeper line, let's say. So it's not that exciting here yet. Maybe that's this line. Maybe that's just x. Now we can play around with like parabolas a little bit. So maybe you have like a quadratic function like this. Okay, fine. And so maybe this is like the quadratic function. Okay, I've drawn it really poorly that I'm gonna have to add things. I don't know. I guess this is like x minus 2 maybe squared plus 1/4. I don't know, something like this. Now let's see. So the weight. What are the weights here? The weights are like 1/4 and a 1. There's a 1 here. Maybe I have to make that clear. There's like a 1. There's a 1 here. Now what happens if I increase this weight? Well, it's kind of the same effect. The parabola gets like more sharp. So maybe this is the parabola like 2x minus 2 squared plus 1/4. Okay. And then in general, what you're going to see is that if you take more, like let's say the 3rd degree polynomial now, if you take a 3rd degree polynomial that looks something like this, okay, I have no idea what this equation would look like, but let's just say for some reason it's like x cubed plus, I don't know, x squared plus x plus 1. I have no idea what it is, but like these will have weights in front that are like, okay, maybe I put them explicitly. They're 1, 1, 1. And the thing I want to point out is that you can see that this thing is kind of made out of a square term and a linear term. And in general, if you were to scale this cube term, you end up the cubic behavior being more extreme. Okay, and so if I were to then increase these weights, so let's say like the values of 2, you get a more extreme kind of function, maybe something like this. And this function would maybe be something like 2x cubed plus 2x squared plus 2x plus 1, let's say. And so the intuition I want you to build is that if you want these kind of extreme, curvy looking functions, the weights are going to turn out to have to be quite large. First of all, you're going to at least need the cubic term and the quadratic, like the 4th order term and so on. So that introduces extra weights to begin with. Like just compared to the line, you can see that this function has a new weight here and a new one here. And like this part is maybe the same, sort of. So 2 things happen, right? Which is like if you end up with a higher degree polynomial, you end up with new weights, scaling the new terms. And if it has very like extreme kind of curvy behavior, those weights turn out to be very large, okay? And so in general, let's just write this down. So if I let my parameter vector, the weights, equal to W naught up to, and we've seen this, which is, it goes up to W, and then P bar was like the number of weights we have when we choose a polynomial of degree P. And since we started at W naught, there's actually going to be P bar minus one of them. And this is an element of what we've seen already is R to the P bar. Okay, so let's suppose we have these weights. And so there's this observation, which I was telling you about. Which is large values of W naught kind of up to W P bar minus 1 leads to a more complex predictor. And so I'm going to call this predictor like f of p, let's say, of a vector. And that'll be this phi of p we've seen, which is mapping your input to the polynomial. Right? This thing would have been like, this thing would have looked like phi of subscript 3, because it gives you degree 3, times the corresponding transpose times the W vector. Okay, that's the observation that hopefully I've like sort of motivated. This is observed. And so you can see now that like if we don't want such extreme behavior, if we don't want such like complex, let's say like if we don't want this thing to extremely overfit our data, because it seems that if we allow such like extreme curves that can overfit the data, we're going to want to limit, right, the kind of the size, let's say maybe the sum or the sum of the absolute values of these weights or something like this, right? That's what you're going to want to do. And so that motivates what you'd first try, which is you'd want to set, you maybe want to change your function class to now have like a dependence maybe on some bound on the maximum sum of, let's say, of these weights, right? You're going to want to add this extra constraint. That like, I don't want my function class to have anything larger than like whatever the sum of weight, any function in it to have a sum of weights larger than some amount. So let's just try to write that down. So maybe we define a new function class like f of p, but we add a new thing which is like some bound on the weights, which I'm going to call, I don't know, c. It's like some constant that you're going to use to bound the maximum sum of weights. Okay. And so this function class is going to look as before. It's going to look like all the functions such that those functions map from r d plus 1 till r such that, okay, this is such that f of some input x is equal to phi p of that input x transpose w. Okay. And we had this thing before where this w was, of course, an element of r of p bar. And now we add one more condition. Maybe that's why I should make this bigger. And that condition is, and, okay, so we're going to want something like this, which is like the sum, okay, from j equal to 1 till p bar minus 1. All I'm doing is I'm looking at these things, and okay, maybe we'll start with trying to do this for j equals 0. So you look at all the indices, and you want these things to be small. So what you can do is you say, okay, I want them to be small, but like sometimes they can be negative, and then negative would be kind of weird because it would subtract out things. So like really you want the absolute value of this. So you want to sum up all the absolute values of these wj's. Okay, and all that's doing is, as we saw above, is like it would just take 2 plus 2 plus 2 plus 1. And maybe to make it more clear, like maybe this was minus 2. And so what you do is you don't want this minus 2 to cancel out the effect of this 2. So you say like, okay, like really what I care about is the absolute values of each of these terms. Okay, so people will use the absolute value in here. And an alternative, which we're going to use because things will be somehow better. And we'll get back to the absolute value kind of later, and this is totally fine as well. We're just going to square this, which is another way to make it a positive value. Okay. And we're going to say that we're going to want this to be less than or equal to our value c. Okay. And now based on like the, okay, and maybe to make a little bit more space here. So you have this property and then this. And are based on our observation above, what we should think is now, well, first of all, this function class, clearly as C gets larger and larger, will contain more and more functions, right? Because it'll contain all the functions that had, like basically it allows more different values of weights, right? So as C grows, it allows more and more functions. And the way you should think of it is as C grows, it allows more and more like complex functions, which are these ones with larger curvature and more complex looking. And as you make C less and less, it will allow for like at some point something like you can't have much more than like a line because your weights are really limited, like if you set C to 1 or something. Okay, so that's how you should think of this. And now the procedure would look something like this, which is instead of sweeping over P, right, make P really big, make it like 20. So you have all the complex polynomials you could ever want. You're allowed to set all the weights, and so you'd have up to like x to the 20 here. And then all you're doing is now you're changing the parameter C. And C is just a real number, right? It can be any value you want that's positive. Maybe I should add that constraint. So the other is C is strictly greater than 0. Any real number greater than 0. If you set this to 0, you always get the all 0 function. Okay. And okay, so that's the idea you should have in mind. This is not quite regularization yet, but it's like it's building the intuition you want to have. Okay. So now what's like, so yeah, you could do this. You can, the nice thing about this is it gives you a nice continuous variable you can now sweep over, and you can pick whatever values you want for that. And now you can plot on this x-axis all sorts of different values. And let's say you find that, oh, in this region, like you plot, I don't know, you choose some like parameters for C, this would be C now, and you find, oh, this is where I'm doing well. Maybe you then want to like narrow in and find exactly like what is the area. Maybe it's somewhere, if I like narrow in here, I'll find that actually the curve looked kind of like this or something like that. And so maybe this is the point I wanted. So you can kind of like start narrowing in on like things between these two values and so on. Okay. So hopefully like it makes sense that having like a continuous variable to pick between is more helpful than having these discrete polynomial degrees. And to make it even more extreme, like suppose that this value is this, and then this one was like all the way down here. Or actually, never mind. Like let's say like there was some weird polynomial function that was something in between a third or fourth degree polynomial, which like didn't have all the fourth degree polynomials, but had some of them. And somehow that one, for some weird reason, had like a loss that was down here. Well, there's no way for you to kind of like construct it in a logical way and so on. But with the regularization thing, you really can start like narrowing down and searching over this space, and then you maybe will find that somewhere here there's like a better loss. Okay. Now I'm going to mention, okay, two more things. One is just like to clean up this thing, because so it turns out that this 0th index is just the it's like the y-intercept point. And that turns out to really not add any complexity to your functions. It just moves it up or down. And so you don't want to penalize your function for having that large. And so you don't use j equals 0 here. You always use j equals 1. Okay. So you don't want to penalize your function for being very large, because maybe it's just all the values like over here. And so having a function like this, which is very simple, would be penalized because it has a very large y-intercept. Okay. So that's one like kind of housekeeping item. Okay. The second thing is now, let's try optimizing over this function class. Well, we have what is called a constraint now, which is you want to minimize over functions of this form. So we plug that in to remember that empirical risk, and we'd see, oh, we need to search over all these parameters W. And it was really nice because remember before we had something like, you want to find the argmin W, and now here, right, it was W in R P bar, and this really could be R P bar. And like by R P bar, it means like the first W could have been like 1,000, and the second one could have been 1,000, and so on. There was no constraint on how large the W's had to be. And then it was like this L hat of W thing. But now we have a constraint, which is we actually have to like take the argument of this, and what people would write is something like subject. Maybe we'll write here. You want to subject to, and this is called like a constrained optimization problem, and it would be subject to this property. Okay, and you can do this sort of efficiently, but it takes more compute to solve this kind of problem, this constrained optimization problem. But there's ways to do this, and you can do this. But it turns out that it would be really nice if we didn't have this constraint. If we somehow just had to minimize, you know, like an objective like L hat. If we could somehow like move this constraint into this objective such that we just had one function we needed to minimize, because we know how to do that very well. If we just had W in this set and there's no constraint and we just had a function, maybe something different than L hat plus some like extra thing, that would be really nice. Then we just use all the same techniques as before and we'd be done. And that's where the normal standard way of viewing regularization comes in. Okay, and so the idea is now, let me maybe rewrite this L hat explicitly to make it kind of clear. So here this L hat, right, was this is the estimate, the empirical risk. It was the, take the average over your data set, the sample mean, I equal 1 to n, of your loss of your function. Here it is of the form phi p. And let's keep things simple from now on and just use d plus 1. And you can imagine it just naturally extends the same way with phi. So we're going to have, okay, maybe not. Let's do p bar. Okay, phi p of your xi vector, right, your data point, with w vector. This is transpose. That's your predictor. And you would compare that to yi. Okay, so that was what we normally had. And so now this is how we're going to move this constraint into the objective. So you want to make this thing small, right? And large values of this are bad, is really what this constraint is saying. And it's really bad if you're larger than C. And so we're going to somehow relax this constraint to say that, well, we just don't want these things to be large. And so that's going to cause us an extra bit of loss, an extra bit of like, we're going to suffer due to this. And so if this is our objective, we're now going to add an extra term to the loss, which is going to penalize these large weights. Okay, and that should be exactly interpreted in this way that we've seen right now, which is, so we're going to add this. And now we remove this. We don't need this. And we have ourselves a optimization problem where we need to minimize something that looks like a function of g of w now. Which is wonderful, because we've already learned how to do this. Because we've chosen the squared thing in particular, you can see that taking derivatives is going to be really nice. If we chose the absolute value, it's still fine, but taking derivatives is unfortunate. And it's convex, it turns out, that you can show that like this thing, since it's convex, and a squared function is convex. If you add two convex functions, they're still convex in the multi-dimensional case too. So this is still convex, beautiful. And it's convex. You can take derivatives of this, beautiful. That's why we're picking the squared one here instead of the absolute value. And this is called, okay, so this term is like penalizing these weights. And now you want to like we lost the C, right? We used to say, oh, we want this to be less than C. The larger the C is, the larger the weights can be, the smaller it is, the less complex. So we're going to want to actually introduce somehow like, I guess the thing that parallels C, but for this like relaxed version, which is going to be a scaling parameter called lambda. And this is called your regularization term, or your regularization parameter. Okay. Right. So that's your regularizer. If you make this larger, that should be thought of as the same as making C smaller, because larger lambda means you suffer way more loss for making these weights large, which is equivalent to saying, I really do not want these weights to be large, meaning C should be really small. So they have the inverse relationship now. Okay, so Small lambda means very expressive function class. If you set lambda to 0, you get just back the original loss. If you set lambda to be very, very large, you're basically can't set the weights to anything even slightly above 0. Like, you really are limited to making them just slightly above 0. Which at the end, in the extreme, is going to be you can only set it to a line like this, because the y-intercept is not penalized, but as soon as you give it even a little bit of slope, you get penalized for the weights. Okay. So that's how you should think of those extremes. And just things to note about terminology now. Okay, and another thing is this is often divided by n so that the scale doesn't blow up. Okay. And also so that derivatives are going to be nice to deal with in a moment. Okay, so we have this. This is like called, this term here is called the regularizer. And notice that this, as we have said, doesn't use W naught. Okay, and then lambda is going to be an element between 0 and infinity, and it's called the regularization parameter. Okay, that was a very long story of defining this whole process. And hopefully that makes the regularization idea not feel like something that just came out of thin air, but is like very principled, and like you can see how you would want to do this based on all the stuff we've already learned. Okay, and all that's left now is just to minimize this thing. That's all we're going to do. And then we're basically done. And so to do that, I just give this thing a new label. I'm going to call this thing, this is like an L hat. It's like the thing we've seen before, right? But now this L hat is going to depend on lambda. Okay. And we fix the P beforehand. So technically it depends on P, but like you should think of like you make P very large, and then the thing you're going to kind of care about is lambda. You're going to change lambdas as you sweep over things. Yeah. So is the question about this indexing? Yes. So recall that this indexing is over data points. So there's n data points here. So we're indexing over data points. While this indexing is over the dimension of your parameters. So P bar minus 1 is totally different from n. And this would be like, you could explicitly write out this dot product as a sum over the same size as well. So I could explain just maybe very briefly, this thing could be written out as a sum from j equals 0 till P bar minus 1 of the corresponding terms above, which would be like phi of P, and this is going to get ugly, but xi. So I is for the data point, and then this thing has an index j, so right, because this guy's a vector, so it'd be the jth index multiplied with wj. So yeah, so these j's, we're going to use j's, and we've used this before to go over kind of indices or dimensions of our parameters, while we're going to use I to go over indices of data points. And so these are different. Okay. Yeah, so that's our new loss. It's called like a regularized loss. It's not quite the empirical risk anymore. It's the regularized empirical risk. And so we're not really quite doing empirical risk and minimization anymore. We're doing like empirical regularized risk minimization. We're not going to write that out any more than that. Yeah, so the loss is a little bit different than the original loss. And then there's all sorts of ways you can talk about, well, you're minimizing a different thing. How close is this to your true loss, and how much error do you suffer? And we're not going to get much into that. But yeah, the ideas are kind of like what we described above. Okay, and so now we're going to want to minimize this L hat guy, right? L hat of lambda, instead of the original empirical risk, the original L hat of F. And this process with this squared thing is, well, this whole argmin minimizing thing is called, I should also call like, this is called ridge regression. I'll just put it here. So this is called ridge regression. If instead we had like an absolute value, which we will see a little bit later in a few lectures, that would be called lasso, L-A-S-S-O regression. It just changes the type of regularizer. And then there's more type of stuff that people do. But another active area of research about how to regularize and how to penalize weights. And maybe you shouldn't penalize exactly the weights. And okay, that's a story. Okay, so now let's solve this problem. So we're gonna want, we're gonna want the W hat vector now, which depends on lambda, which is equal to the argmin W from R. And just from now on, let's just let's set P to equal to 1. Okay, so that implies that this P bar is equal to D plus 1. So that I don't have to keep writing phi P everywhere, and then you can imagine how everything works the same way with phi P. Okay, so maybe I make that in blue. Okay, and that's what we want to minimize, and we know what this L hat term is. Oh, L hat lambda of W. Okay, so let's do this. So similar to what we've seen before, there is a closed form solution for this, and it goes really through the same procedure as before. You just need to get the partial derivatives of this extra term, and the beautiful thing is it's just an additive term. So all the derivatives we calculated before, and we're going to do it for the gradient as well, it's just going to be like the derivative, the partial derivatives of this is going to be the partial derivative of this, which we already know what it is, plus the partial derivative of this. And so yeah, we're going to do these partial derivatives. You can then set it to 0 and solve, and you get the closed form solution. And the closed form solution looks almost exactly as before, except there's just like a plus regularization term in that like A matrix. Okay, just for those like you remember there was like this A matrix that looked like X I equal 1 to n of xi vector, xi transpose, this outer product thing. And then we took its inverse and multiplied it by the corresponding B vector. Well, it turns out if you solve this thing, all that's going to change is this A thing. Maybe I'll call it A lambda becomes this plus lambda. Yeah, that's it basically. So we're not going to work that out, but turns out like you really would go through the same process. We're just going to do the version of the gradient descent. Okay. And once again, it's beautiful. Like there's a closed form solution. Things are convex and all that. Okay, so let's do that. We want to do gradient descent to solve for this. So that means we're going to be solving for like W of iteration t plus 1. We're going to do these gradient steps. They're going to look like this. Some step size. And then the gradient of L hat lambda of W of t. And the only thing that's changed is now we have a new function we need to take the gradient of. But luckily, as I said, that function is just the previous gradient plus an extra term. Okay. And so let's remind ourselves some things, since we may have forgotten. This gradient, right, is just this vector of partial derivatives. So it's the partial derivative of L hat of lambda with respect to W0. The partial derivative of L lambda with respect to W1 up to, maybe a copy and paste to make it clear that it's the same term, up to WD transpose. So that's your gradient vector, just these partial derivatives. All we need to do is calculate these partial derivatives. And Let's look at how we did that. So we're going to need to take the partial derivative of this for every single wj index. So that's the partial derivative of this plus the partial derivative of this, and we've done this. Notice that this, so we're going to need to do it for every single j from 0 till p bar minus 1, or in this case up to d. This has nothing to do with j equals 0. So this is not existent for j equals 0. So for the j equals 0 case, it's the same as before. So there's going to be two cases now. Okay. So the partial derivative of this loss with respect to w0 is the same as before. So it's actually the same as what we had for L hat, which is the same, I mean, I'm just telling you what it was. It was 2 over n sum I equal 1 to n of xi transpose w vector at, okay, w vector minus yi xi. And here, this is what would index the dimension of xi. Xi is a vector. So this would be j, but since j is 0 here, we put xi is 0. Okay. And then for all the other values, it's going to be like 1 to d in this term. But we had an extra term we need to take the derivative of. So let's do that. And that turns out to be very straightforward, actually. Let's do this. So for j equal to element of 1 up to d, so for all the other values of w, it's a little bit different because now we have this extra term, the regularization term. And so this will become, well, if we look upstairs, the derivative of this thing, which maybe I will even make it clear here, this is just L hat of w that we've seen before. And so this is going to be the partial derivative of L hat with respect to wj, which we know what that is. It's just going to be the same as this, basically, plus the partial derivative, and I'll write it like this. Instead of giving it a name, it's going to be the partial derivative of this kind of like function with respect to wj. Okay, and luckily this is very easy to compute. So this becomes, so the first term we know, and to make it absolutely clear, it's literally the same as what we just saw, except with xi0 replaced with the j. And maybe, let me just make that clear. This is where the j is coming in. And now let's take the derivative of the next term. And we can just do that visually. So we have this function that's just the sum. This is d now. It's the sum of dwj squared terms. We want to take the partial derivative of with respect to just the wj. So think of it as like this multivariate function of d variables. We're just taking it with respect to this variable wj. All the other variables are treated as constants, so they have nothing to do with anything here. So it's just the derivative of wj squared. Oh, and maybe I should make this a little bit more like this. This can be confusing. Okay, why can this be confusing? Because I'm taking the partial derivative with respect to j here, and then I have a sum going from j, and these look like they're clashing, which is true. And so to fix that, I use a different index here, which I will use instead of j, I will use k, just another index, so that you can see exactly what's going on. So k is going from 1 to d. And I'm gonna, I want to do it for all these wk's for every index. And this is our function. And so now I want just the wk term. And so that would be like whenever j, j equals to k at some point, that's only that term that we're focusing on. And so that would just be what is the partial derivative of lambda over n, which is a constant, times wk squared. Well, that's just 2 times the expression, right? So it becomes 2 lambda over n of wk. Because all the other values of j that are not equal to k are just treated as constants. and they're just equal to 0. Okay. So that's it. That's your partial derivative. And the same holds for when you have higher order polynomials. You just replace this kind of xi transpose with phi p of xi everywhere. And yeah, so now you would just, this is your new algorithm with regularization. And maybe to make this clear, I am going to add, I'll give you the pseudocode, which the way to do this, I will just make it, I'll just actually, oh, how did that happen? Wait a second. Whoops. Okay, I'll just copy and paste it in to save a lot of time from this, because I wanted to say one more thing that I thought might be interesting. Okay, where's the pseudocode? So all I did is took the pseudocode of batch gradient descent, and we'll see what we add in a moment here. Okay. Great. So this is batch gradient descent. Forget about this part. That's going to be the new part. Okay, so this is literally just a copy and paste from the batch gradient descent we've seen up to now. Remember, there's batch gradient descent, and there's a constant step size. You have this data set. You have your step size. You have your number of epochs. You have your random vector. You initialize it randomly. And then you just calculate the usual gradient of the empirical risk, and then you do this update. Everything's the same as before. Now we somehow need to incorporate this new gradient we calculated, right? So first thing is, let's rename this learner. So it's not the batch gradient descent linear regression learner with a constant subsize. Now it's going to be, I guess, there's going to be and regularization. And regularization. There's going to be another parameter now called the regularization parameter. So you can see how there's all these parameters that we end up introducing. Before there was the mini batch size, and of course you can do mini batch gradient descent in the same way. And now we're introducing this new parameter called the regularizer, the regularization parameter. And oh, did I not? Oh, I guess I should probably end up, okay, good. So pseudocode. Yes, you have this regularization parameter. Now all we have to do is calculate the gradient of the new L hat lambda thing. And if we look above, the way to do that is, well, we need to calculate all of these partial derivatives. What we saw is that for the 0th term, it's just this. And actually for each of the other indices, it's also the same thing. So we can keep the previous gradient calculation, and all we have to do is add this quantity for indices 1 to d. That's all we need to do is, right, take the previous gradient, just add this new thing to. And that's why there's this little gap in here, which is you take the previous gradient calculation, and to it, and to that, you're going to want to add, so plus equals, so you take the previous value, add to it, and you're not going to want to add just at all indices. So I'm going to use Python notation here. You're only going to index from 1 to d. So you're going to exclude 0. In Python, of course, you know, this would be from 2 to d plus 1, because you don't start at 0 in Python, but I'm mapping it to our indexing. So there's a 0 index, okay? And now the thing you want to add is just exactly this term. But this was the term you wanted to add for particular index k. And so you want to transform this now instead into the vector version, which is you would take the w vector and take its indices from 1 to d. Okay. Yeah, that's it. That's all that changes in your algorithm now, is now you have this extra addition for indices 1 to d, and the 0th index is untouched, and it just remains as this calculation we did above. Okay, everything else is the same. And the reason this was all interesting is because if we went up So this plot, it would be the exact same kind of story, but now with a lambda in the x-axis. Maybe I'll add it to this part before the pseudocode. So everything would be the same story. Now you change the x-axis to lambda. And now the relationship is not that as lambda grows, this goes. It's actually the other direction. Okay, so remember lambda equal to 0. And we should fix a degree p. So let's say in here we've fixed p equal to 10. So you have a very complex polynomial. And now we're sweeping lambda. And so recall that if lambda is equal to 0, then you end up with 0 times this. So you're not penalizing the weights at all, and you just are left with your previous loss, which is really you're minimizing a 10th degree function class you're using a 10th degree function class to minimize over. And so there we saw that that would mean you have very high variance before. So over here, all the way over here, this is approximately equal to 0 lambda. And over here is very large lambda. So something like 100 would be very large because you're suffering 100 loss from just setting one weight to 1, let's say. And so you would sweep in this like logarithmic manner. So you would sweep over like 110. This turns out to be a good idea. Whoops. That's not right. 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. And here you would have like 10 to the minus 4, but I'm saying like as you go on, you eventually get to something like 0. Okay. And at 0, you really have this error of the 10th degree polynomials. And the story basically remains the same. And you can do all the same stuff with your test set and your training set. And you would sweep over this and you would pick this point. And another thing you can do is then you're like, oh, it seems like this is the good region. And so then you can do another sweep that's more fine-grained within this region. And pick and then you maybe find once again that it looks something like this. And maybe a point down here is better or something. Okay. So that's regularization. And now, since we have a little bit of extra time, I kind of wanted to mention how all of this is a little bit of a lie. And this is not, okay, so I'm going to tell you about something called like double descent, which is that, roughly speaking, it turns out that if you go for a high enough polynomial degree, at least for the polynomial plot, you end up with another drop. And actually, it can go even below this point. Okay. But this is not for marks, but I thought it'd be fun to mention because it like points out some, so I don't know, not graded. I didn't mention this last year, but I thought, well, why don't we talk about it this time? So yeah, what is this whole double descent business? How is this possible? What's going on? And okay, how about I do like the high level story, and maybe we spend a couple more minutes next time on this as well. So you may have, we talked about this whole overfitting thing. And let's look at an example one more time. So I have a data point, another data point. Oh, maybe before I is there any questions about all this stuff before, like regularization and so on? Because this is really the end of this whole evaluating your predictors and picking function classes and stuff like that. Okay, great. So yeah, maybe you have like, I don't know, 4 data. Okay, I think we're back. I somehow clicked the mute button on my little thingy. Okay, I'm just going to briefly re-explain what happened. So the idea was you have, I think, yeah, this is all you need to know. You have these data points. You can start fitting it with like a line that maybe doesn't fit it that well. Then you can try fitting it with polynomial degree 2. That fits it better. Polynomial degree fits it better. Then it turns out that if you have 4 data points, a polynomial of degree 3 will be enough. And in general, if you have n data points, a polynomial of degree n minus 1 will be enough. Okay, and you can keep taking this to the extreme. And what we've learned so far is if you make the polynomial even bigger, you're really going to be screwed with this whole overfitting business, because you're going to end up with things that look ridiculous. You're going to have like functions that look like this. And that is indeed true. If p is like 10, you can't have a function that looks like that, or even worse. Okay, and why is this interesting? Or like, where is this going? Well, when people started using these neural networks, and we use them now, they're giant. They have literally billions and sometimes now trillions of parameters. And you do not have trillion data points. Okay, so you literally have less data than parameter. And that is really bad, what we thought, at least before. And so it's called like this over-parameterized problem. Your models are over-parameterized. They have too many parameters. And so in general, you can see that this could be really bad, because it could pick a function that looks like this. And the thing I want you to note is as soon as the degree of your polynomial goes above n minus 1, there is infinitely many choices of the polynomial. So let's say we chose n to be, or p to be like 10 here. Well, then there was this purple line that could fit it. Maybe there's also this line, or this curve that fits things perfectly. And there's also this guy here. And this orange one doesn't look too bad, right? It actually somehow is better than the green one, because it doesn't need this like cubic behavior that has to go on forever. It can really like balance out here, and even maybe I should make this even more extreme. Maybe the real best thing is like something like this, and so it can really be like this, and then just quickly jump here, and then like go here, and then maybe just quickly jump. And so this might be actually a really decent fit. So the point is, if you increase the polynomial degree, you really can get a function, if you pick the right one that minimizes, that fits the data perfectly, you really can get quite a nice and smooth one. Okay. And the rough idea was that like, well, okay, let me just finish this with. So the rough idea is like, what's going to happen? Like, if we have this really high degree, which one is going to be chosen? Okay, so like, you could have chose this purple one or this red one, or you could pick this orange one, which is actually better than before. And it turns out that gradient descent, the way it works, actually implicitly chooses the line, or the curve that is somehow the smoothest. Or in other words, these purple and red ones would have really high sum of like parameters or weights, and this orange one would have a much smaller sum of weights. And gradient descent will actually pick kind of the curve out of all these infinite choices that has the smallest sum of squared weights implicitly. And so it turns out that like you might not even need any of this regularization. People still use it. And as you increase the polynomial degree, it implicitly does this kind of behavior. And we'll talk about that next time, but you'll see a curve like this. And then the double descent idea is that as you keep increasing, it keeps going down. And maybe, yeah, I want to spend maybe like 10 more minutes next time, and then we'll get into this maximum likelihood estimation. Okay, well, I'll see you on Thursday.